Good evening. Does it work? I don't think it is either. All right. Good evening, ladies and gentlemen. My name is Cynthia Cuno from JPL's Public Services Office, and I'd like to welcome you all to tonight's installment of the Von Kármán Lecture Series, and also extend a warm welcome to our viewers out on the web. Tonight's lecture will discuss how one of NASA's future spacecraft, the Orbiting Carbon Observatory, will be the first to provide space-based observations of carbon dioxide with the resolution needed to characterize the production and loss rates of this important gas. This data will revolutionize our understanding of the processes regulating atmospheric carbon dioxide, enabling more reliable forecasts of climate change. Tonight's lecturer was born in New York City and was a frequent visitor of the World's Fair. He grew up enjoying math and classical literature, but knew he was destined to become a scientist when he was introduced to the quantum mechanical theory of atomic structure and electron energy levels in the 8th grade. He attended Duke University, graduating in 1986 with a degree in chemistry and history. He then went on to study at the University of California, Berkeley, obtaining a PhD in physical chemistry in 1991. In 1994 to 1997, he was a National Research Council Research Associate at NASA's Jet Propulsion Laboratory, and in 1997, he became a faculty member in the Department of Chemistry at Haverford College in suburban Philadelphia, where he conducted an active research program in high-resolution molecular spectroscopy with undergraduate students. Currently, he is project scientist in the Earth Remote Sensing Science section at JPL. And since 2001, he has served as the Deputy Principal Investigator of NASA's Orbiting Carbon Observatory mission, managing the OCO science team and learning about the interface between global climate change science and policy formulation. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Charles Miller.
Thank you very much, Cynthia. Are we on? Good. It says on. There we go. Okay. Thank you very much again, and thank you everyone for coming out this evening. It's great to see such a large and energetic audience come out on a Thursday night. And I wish I could see everyone who's out there in web space, but we'll just have to go along with that for the moment. This is going to be really, really fun. I'm glad you're all here tonight, and I promise to talk about a hot topic and cool science. So we'll get a little bit of each of these in, and we'll throw in some information about the Orbiting Carbon Observatory at the same time. So the hot topic, climate change and carbon dioxide emissions. It's relatively difficult nowadays to go more than a week without reading or hearing in the news about something related to climate change and carbon dioxide. And in fact, we'll see in just a moment that you don't even have to go as far back as a week this time. In terms of cool science, we have the ability to, with this mission, with the Orbiting Carbon Observatory mission, this is really kind of great because we're starting from fundamental molecular properties, and we're going to use those to build up an idea, a concept for a measurement that actually allows us to study climate change, which is a global perspective science question. So starting from the most basic fundamental molecular properties, we can understand something that's happening for the entire Earth system. That's really, really neat, and I hope you'll come along for that fun ride. We're then going to talk about how the Orbiting Carbon Observatory, OCO, will measure carbon dioxide from space. And then there's actually a lot of interesting applications of OCO information. And so we'll look at some of the ways that OCO can be used to monitor greenhouse gas emissions. And we'll talk a little bit about carbon footprints. And I encourage you all to think about what your carbon footprint might be. And I'll risk sharing what mine is with you. So with that, I said one wouldn't have to go very far back into the recent past to find out about carbon dioxide. And if you go back to a week ago Monday, the Supreme Court announced their decision with respect to a case brought by the state of Massachusetts plus several others against the Environmental Protection Agency. So here we have the Supreme Court and all the powerful thinkers in there. And it wound up that the Supreme Court ruled that the EPA did in fact have the authority to regulate carbon dioxide as a pollutant. So carbon dioxide and other greenhouse gases could be regulated by the Clean Air Act that the EPA was already responsible for. And that's, I guess, our most recent motivation. I'm sure that there will be others, but If we go back a little bit further, we can find that as far back as 1896, in the Philosophical Magazine of the Royal Society in the United Kingdom, we have an article from April of that year. So it's April now. We go back April 1896, and we find out that a very famous chemist by the name of Svante Arrhenius is studying the influence of carbonic acid or carbon dioxide in the air upon the temperature of the ground. And that sounds really, really, really familiar. In fact, that's more or less the same thing that we're talking about right now. And we're trying to understand how carbon dioxide interacts with the Earth's climate system and what that might portend for the measurements of both surface temperature and carbon dioxide into the future. And let me just, it's hard to read this. This old print doesn't scan very well, so I'll read for you. A great deal has been written, remember this is 1896, so a great deal has been written on the influence of the absorption of the atmosphere upon climate. Okay? That's exactly the theme of tonight's discussion, and already more than 100 years ago, we have people thinking a lot about this. So it's really neat to see that the more and more and harder we think about things, the more we come back to some of the same basic fundamental questions. All right, so now is time for phase one of our cool science. And this has to do with the fundamental molecular properties. And for this, I need 3 volunteers from the audience. I see one young man right there. Come on up. Come on up. We have 1 volunteer. Do we have 2 other eager people? Another volunteer. This young man, would you like to come up on stage and help us out here? We need a 3rd. 1 more. Do we have somebody who, let's see, carbon is mass 12 and oxygen is mass 16. Okay, we have another volunteer there. Excellent. Come on up. All right. You didn't think you were going to come to see interpretive dance tonight, did you? Oh, yes. Jason, why don't you be an oxygen atom? Okay. And you're kind of big and would be good in the middle, so why don't we have you be, and your name is?
Bill.
Bill. Okay, Bill, you can be a carbon atom, and you are?
Abraham.
Abraham. All right. Thank you very much for helping out. Whoops. You can also be an oxygen atom. All right. And those of you who want to join in at home on the internet or in the audience, feel free to just stand up and participate, okay? And just remember, I am a trained professional, so don't try this at home, okay? All right. We have, in fact, our linear triatomic carbon dioxide molecule depicted here, but one thing we're lacking is we have individual atoms. We don't yet have a molecule. So the electrons in the atoms have to reach out and bond to each other. So the carbon atom needs to bond to our oxygens. And in fact, carbon dioxide makes a double bond with each one. So we need you to put both hands in. Yes, Abraham. And Jason, you. Okay. Now kind of stretch out a little bit so we get that nice linear molecule. There you go. All right. Now, and I can do this as well, or you can try. You can pretend that your fists are the oxygen atoms and your torso is the carbon dioxide, or the carbon of the carbon dioxide. And now we're going to go through the fundamental vibrations, the intrinsic motions that make carbon dioxide absorb infrared light in the atmosphere. So the first one is a symmetric stretching motion. So I need Abraham and Jason to kind of come in together at the same time. Yes, walk in there, and now you get to walk back out, and you get to do this maybe a little faster. And this is the symmetric stretching motion of carbon dioxide. Excellent. All right. Bill's having a lot of fun. Okay. Now, that is one of the vibrations. That's the first vibrational mode. Now, there's another one, which is the anti-symmetric stretching mode. So this time, it's a little more complicated. Abraham, why don't you stay out here? Jason, get in close. Okay, now Jason, you back up and Abraham go in. There we go. And it winds up that the carbon atom never really moves very much in these, but you go back and forth and back and forth. Now it's very interesting here. Let's freeze frame right here, because as opposed to the symmetric stretching motion, where the electron distribution remains symmetric the entire time, you can see here that one of the oxygen atoms is much further away, and one of the oxygen atoms, we need to turn you around so people know you're an oxygen. There we go. Okay, so one of the oxygen atoms is very close. So we have different electron densities. And what happens is that creates a net electron dipole moment. And that dipole moment, since it changes, now let's change the molecule around, the other phase. Very good. Now it's actually pointing to this side where the electrons are closer together. And so this dipole moment that changes is what induces the interaction with light and causes this motion to absorb infrared radiation at the wavelengths that correspond to the energy of this motion. Okay, so let's go through one more time. Can we do a little asymmetric? Very good. Oh, you guys are great. Okay, thank you. Now, fully extended again. We've got one more vibrational motion. This is the bending motion. So here, Jason, we need you and Abraham to walk forward and now go back behind the plane. Very good. Yeah, are you stretching out well? Yeah, this is better than Pilates, isn't it? Okay, and so that's the bending motion. Now, the key thing to notice about the bending motion here is it breaks the linear configuration. So if we can come out full amplitude here, we've got now a V-shaped molecule. And if you do the calculation of where the dipole moment, the effective dipole moment is now pointing back this way. And if we turn around the other direction, we've got another one. And now we've got a dipole that would be pointing forward. And so this also induces a change in the electronic distribution, which is, although symmetric, it's no longer pulling evenly. And so we'll have a dipole here. So this motion also absorbs infrared radiation. All right. So that's our great interpretive dance. And let's give everybody a big round of applause. Thank you. And, oh, no, please keep your atoms and also have your very own OCO pencils, complete with lots of carbon. Okay. Thanks again, guys. It's great. Okay, so we've got some fundamental molecular physics now. We've got the symmetric stretch, which winds up being infrared blind. It doesn't do anything in the infrared. But the anti-symmetric stretching motion and the bend will absorb infrared radiation because that wavelength of light has an energy that corresponds to these molecular motions. And where that energy is absorbed, you're actually going to see a dip taken out of the spectrum, which, if we go and look at an atmospheric spectrum, we can now see that not only for carbon dioxide, but for ozone and other molecules. So here's a big chunk taken out of what we would expect to be a smooth curve for the atmosphere of the Earth. You can see the big infrared absorptions here due to carbon dioxide. And that happens at this characteristic energy for the bend, in this case, associated with a wavelength of light of 15 microns. There's another motion of CO2 that would happen out here at about 4.3 microns, and some others that happen further on. And it happens for many, many molecules: water vapor, ozone, nitrous oxide, all of the greenhouse gases that you hear tell about, methane. And so you can see this in the spectrum, and this is exactly what gives rise to the greenhouse effect. Because what happens in the greenhouse effect is that radiation from the sun can come into encounter with the Earth. Some of it bounces off the top of the atmosphere via clouds or just scattering from the atmosphere, but a large majority of it makes it all the way down to the surface. There, it's absorbed by the surface and re-emitted as heat. And what we experience as heat, if you put your hand down and feel over the street or over the sidewalk on a warm summer day, that energy is actually infrared radiation being re-emitted, and the interaction of that radiation with your hand is causing vibrational excitation of the molecules in your hand. And your nerve impulses register that sensation as heat. You could do it over anything that's hot. You could also do it over something that's cold. So if you put your hand over a large block of ice, you would feel the slowing down of the vibrations and the lessening of the amplitude of the vibrations in your hand, and we interpret that as feeling cold. So it's either the increased or decreased amount of infrared radiation in the atmosphere. So what happens to a lot of this, some of the visible and UV can scatter back out too, but the stuff that's absorbed and gets re-emitted as infrared radiation can go back into the atmosphere, where the trace gases in the atmosphere, these so-called greenhouse gases, can absorb part of it. So some of it goes back out, but that which is absorbed gets re-emitted. And it doesn't really have any preferential direction in which it's re-emitted. So some of that gets re-emitted back out to space, but some of it comes back down to the surface, where it can be reabsorbed. And then you get this kind of hall of mirrors effect, where you get the infrared radiation being absorbed, re-emitted by the surface, absorbed by the atmosphere, re-emitted, and some small fraction of it keeps coming back to the Earth. Now, if we were to stand back and look at the Earth as a planet from the perspective of the sun and calculate what we would expect the temperature of the Earth to be based on radiative balance, just the amount of sunlight that hits it, assuming that all of that sunlight would be then re-emitted as radiation, we would calculate that the average temperature of the Earth should be something like minus 15 degrees centigrade. Minus 15 centigrade. Is there something that's very interesting about that temperature? relative to some other temperatures you might know on the centigrade scale?
Freezing.
Anyone? Freezing, I heard over here. Right. What freezes?
Water.
Water would freeze. So at minus 15 C, as the average Earth temperature, we would expect, on average, that all of the water would be frozen into ice, and we would live on a giant snowball or ice ball planet. However, the average temperature of the Earth is approximately 15 degrees C, plus 15. So we have a natural greenhouse effect of about plus 30 degrees C, and that is the blanketing or insulation or greenhouse effect that the atmosphere is providing. Okay, so we have a natural greenhouse effect. Most of the water is liquid. That's very good for us. Makes life a lot easier. Makes ice skating a little bit more difficult, but on the whole, I think biology and Mother Nature would take that as a big plus. So there's the greenhouse effect. And the greenhouse effect is, again, just induced by that physical absorption of the molecules. Okay? Their vibrational motions are causing them to absorb this infrared radiation and then re-emit it, and that trapping is what's leading to the greenhouse effect. So we've already got our fundamental science questions, now part of the cool science, because we can actually go and look at things in the old atmosphere, the paleoclimate. And we can do this by drilling down using the same techniques that the people drilling oil wells use, and take out cores. And so here you can see the drill being opened up, the drill bit being opened up, and the ice core being extracted. And this is from Antarctica. This is the Vosloh Center. They're drilling down through thousands of meters of glacial ice there, and they're pulling out these cores and learning about what was the Earth like in times many thousands of years ago. And the reason for that is you can accumulate snow and ice and kind of press down on what's been there before, and it gets more and more compacted. So as you go down into a glacier, the deeper you go, the further back in time you're going. And as the ice is forming, there are some small microscopic air bubbles that are being trapped in there. So you actually get samples of the ancient atmosphere or records of paleoclimate that can be extracted if you have a way to go down and get these cores from far down in. And here, for example, is a section of one of the cores. So this is looking along the core here, and you can see very easily the bright dark striations from different ice levels. Okay, and this one is taken from a core, I believe this is from Greenland, at a depth of about 1,800 meters, which corresponds to 20,000 years ago when this was formed. So going in here, we can take out the air that's in these trapped ice bubbles and learn about the atmosphere from 20,000 years ago. And if one does this, here's the kind of information that you get. In fact, this ice core record at Vosloh goes back over 400,000 years. 400,000 years ago, we can learn about the atmosphere. So what are we looking at here? Well, this is the measurement of CO2 in concentrations of parts per million by volume. So one CO2 molecule, 1 part per million is 1 CO2 molecule per million molecules in that atmospheric sample. You can see that between 180 and 280 or so parts per million winds up being the natural oscillation range. And during this time period, there was a lot of ice age forward-backward motion. So we're going into the ice ages, we're coming out, we have warming. And you can see that from the temperature record that can also be extracted from these ice cores. Now notice, as temperature goes down, the CO2 kind of goes down. And as the temperature goes up, the CO2 goes up. And they track and correlate very nicely together. However, as we look in the more recent past, say maybe out to about 150 years ago, we notice something quite extraordinary. The CO2 record begins to rise, and by about mid-1900s, it's rising rather dramatically. Also, if we look at the temperature record from about 1850 forward, we see that it goes from a normalized value of about minus 0.4 C up to about plus 0.6 C at the present time. So a change of about 1 degree C that's taken place in the last 150 years. Does anyone know what was going on around the middle of the 1800s that might have triggered one of these very interesting events? I see a gentleman there. Yes, the Industrial Revolution. And why would we expect to see changes in the carbon dioxide emissions into the atmosphere associated with the Industrial Revolution? Factories, coal. Any others? Population growth. All of these things, right? automobiles, where all of these are contributing. And one of the largest things is not just the coal, the natural gas, the oil, but it's the combustion of all of those fuels. So converting them from their native carbon or hydrocarbon sources into carbon dioxide that's in the atmosphere. Again, notice the very strong correlation as things are going up, up, and away. And we now have the modern era of carbon dioxide measurements. Charles David Keeling, a very, very clever man, during the first International Geophysical Year in 1958, started a series of measurements of carbon dioxide, very accurate measurements of carbon dioxide from the observatory on the top of the Mauna Loa volcano in Hawaii. And he went to Mauna Loa because that's an area where he was certain he would be able to sample very pristine background air. So no pollution, no contamination by local sources of carbon dioxide. He was certain that he was going to get air that was characteristic of the average background. And you can see that beginning in about 1958, now recall we were talking in the period from 400,000 years ago up to about 1850 or so, CO2 values oscillating between 180 and 280 parts per million. In 1958, it's around 315 parts per million. So we have CO2 concentration on the y-axis, and then we're going to follow time forward on the x-axis. And since 1958, let's see, we went from 315 up to the present. If we trace back, we're at about 380 parts per million. So from 1850 to let's say 1950 to make the math easy, in that 100 years, the concentration of CO2 in the atmosphere went from 280 parts per million to 315 parts per million, a change of roughly 30, 35 parts per million. Since 1950 to, let's say, 2000, okay, another 50 years, not 100 years, we've seen the change in carbon dioxide go from 315 to 380, or a change of 65 parts per million in the atmosphere. Double the rate in half the time, right? We're changing twice as much in half as short a period of time. So that's something we need to be really concerned about, because you recall that there was only an oscillation of 100 parts per million over the last 400,000 years, and now we're talking about a new change of plus 100 parts per million relative to where we were in 1850. And we've got to think about what's going to happen to the Earth's system. How is it going to react? How, especially, is the temperature correlation going to begin tracking with this CO2. One other thing I should point out is these very interesting undulations here. We have another chance for audience participation. What might be causing these undulations that happen on a kind of 6-month time scale? Oh, I heard it from in here. Summer and winter, but photosynthesis. Very good. The plants and all the phytoplankton in the oceans are breathing in and breathing out. So what you're really seeing here is the Earth's respiration cycle, which takes place on about a 6-month time scale, as opposed to our respiration, which is 10 or so times per minute. So instead of 6 seconds, it's 6 months. But you can see exactly the same thing. As photosynthetic uptake occurs, the CO2 goes down. And as you get into the wintertime, as photosynthesis shuts down, and as the plants die and decay and release additional CO2 in the atmosphere, the CO2 goes back up. It comes down, up, and it continues to go. We have a question over here. Yes?
Is that because there's more land mass in the northern hemisphere?
Ah, that's a great question. We can look at these plots from a perspective of sites in the northern hemisphere and in the southern hemisphere, and we can actually look at them as a function of latitude, and it's really quite interesting to look as a function of latitude away from the equator. So are you at a low latitude or tropical, or are you at a high latitude, something that's further away? And what we would find is that you would see a similar pattern in the northern hemisphere for all sites, except that the amplitude would increase and increase and increase as you got closer to the poles. And that's because the growing season there is much, much shorter, but much more intense, because it has, if you get far enough north, you can get up to 24 hours of light during midsummer. And so these plants have evolved so that they can grow very, very rapidly. So the CO2 drawdown is quite intense. Likewise, the amplitude of the CO2 increase is pretty dramatic as well as you go towards winter when things shut down. What's going to happen in the southern hemisphere if I look at this calendar? You've asked the question, I'll pose you a question.
It'd be the opposite.
How would it be the opposite?
Well, you'd have your growing season in the other 6 months, right?
Indeed, because the southern hemisphere seasons are switched 6 months opposite the northern hemisphere growing season. So if we were to make a plot of some place like, let's pick South Africa or Amazon in the southern hemisphere, we would see this same undulation, but instead of peaking in December or January, it would actually be a minimum in December or January because that's midsummer in the southern hemisphere. Likewise, you would see the maximum for the southern hemisphere occur in June, July, August, as opposed to the minimum that we see in the northern hemisphere for those points. Excellent question. And thank you for interrupting me. I'd like to ask anyone in the audience, if you have a question now, we'll have time at the end for more question and answer, but very frequently, it's better to ask the question when it comes up because I can absolutely convince you that you are not the only person in the room who is thinking that question. Okay, so you might be helping out the person next to you if you ask one. All right, so moving onward then. Okay, we have another question here. Great.
In not the last slide, but the one where you have the carbon on the top and the temperature below that, or the one before that, where it was a longer time period.
Sure.
Was the temperature driving the CO2, or was the CO2 driving the temperature? What was the?
That's an outstanding question. Outstanding question, and I thank you for reminding me that I'm supposed to mention that. Because while I did say there was a very strong correlation, it's difficult in these ice layers to get very good time resolution. So it's unclear from this data record whether the CO2 is forcing the temperature or whether the temperature is forcing a change in the CO2. So keeping that in mind, as we, let's go forward to this one and say that I know with great confidence what the CO2 is doing in this time period. And just like you'll hear the financial analysts on the evening news talk about expecting market adjustments based on what's happened to interest rates or some other such thing, I am expecting to see a temperature change because I know that there's a correlation, a very strong correlation on geologic timescales between carbon dioxide concentrations in the atmosphere and the average global surface temperature. So I expect to see a corresponding correction. I don't know which one is driving the other, but I do expect to see them correlate and move together. Okay, does that answer your question? Great, thank you. Okay, so let's then look at the big outstanding science question. Where are the sinks that are absorbing some of the carbon dioxide that's being put into the atmosphere? If we look over here from 1950 to the present, we have, again, the annual emissions in carbon dioxide, which can be tracked basically using fossil fuel inventories. We know that people buy fuel to burn it, either for industrial purposes, for commuting, for cooking, what have you. And these fossil fuel inventories don't last very long. If you buy a tank of gasoline, you don't park your car typically for 6 months or a year. You go out and drive around and you use it. And so what's assumed here is some relatively short times between when fossil fuel like coal, oil, or natural gas is purchased and when it's used. So when it would be converted through combustion to CO2 into the atmosphere. So we can look at this emission rate over time. And if we go to the Keeling plot right here, we can actually do a little bit of math. So don't be afraid yet. But we're going to take differences of these concentrations with respect to time. So what's concentration X versus X1 at time T versus T1? We'll take and evaluate those ratios. And if we look at those, that tells us the amount of carbon dioxide that's accumulating in the atmosphere. And that's shown in this yellow chart, part of the chart here. And so you can see that that's kind of variable. And sometimes it spikes up and we get a lot of CO2 accumulating in the atmosphere. But sometimes, very close by in time, we're getting a big uptake of CO2, not very much accumulating in the atmosphere. And again, here's a little smoothing for the 7-year mean, but you can see lots of spikes, both in the upward direction and in the downward direction. And in fact, at some points in time, the amount of CO2 that stays in the atmosphere is almost the amount that's emitted by fossil fuel combustion. In other cases, it's only maybe 1/3 of what's emitted. Well, if we add all of this accumulation in the atmosphere up, we find out that about half of what has been emitted into the atmosphere from fossil fuel combustion has stayed there. So where did the other half go? Well, carbon dioxide winds up being extremely inert. It has very, very little chemical reactivity. In fact, essentially no chemical reactivity in the Earth's atmosphere. So when it's put into the atmosphere, it stays there for hundreds and hundreds of years, unless, we talked about photosynthetic uptake before, right? Unless it gets drawn into the plants by photosynthetic uptake. And there are also some physical processes where it can be absorbed by soils on the land and also by oceans. Water is a great absorber of carbon dioxide. In fact, if you go out and get carbonated water, you've just got some water that's had CO2 injected into it. Okay? We're doing that slowly but surely to our oceans. We're carbonating them. The CO2 is being absorbed there. So between the oceans and the land, about 50% of the CO2 that's been emitted over at least the last 50 years is being stored. But the problem is, we don't know why the storage varies so dramatically as a function of time, and we don't know whether it's land or ocean, and if it is on the land, is it over Eurasia? Is it over North America? Is it over the Amazon? Where is this taking place? And even furthermore, projecting out into the future, we have a large uncertainty in what this CO2 concentration is going to be because we don't know exactly what's happening now. And because of this strong correlation between CO2 and temperature, we have a difficulty forecasting what our future temperatures might be like or what our future climate might be like. So this leads us into why would we want to do something like measure CO2 from space, which is what the Orbiting Carbon Observatory is planning to do. And I should emphasize here and preempt all of the discussion now about OCO by saying that OCO is not going to be, one moment, the first satellite to measure carbon dioxide in the atmosphere, but it will be the first to measure carbon dioxide with the precision and spatial and temporal resolution that is needed to unlock these questions that we talked about just a moment before about where the CO2 is being absorbed by the land and ocean ecosystems. We have a question in back.
Yeah, do you need more data, or do you need better models, or do you need sort of a theoretical breakthrough, or all of the above?
Okay, the question is, to understand the global carbon cycle, do we need more data? The answer is yes. Do we need better models? The answer is yes. And do we need a better theoretical understanding of what's going on? The answer is yes. We need all of the above. And in fact, I think what I'm going to show in a chart or two is what happens when you don't have enough data. So keep that part of your question in mind, because in just a chart or two, we're going to see what we know about the Earth and the global carbon budget based on the information we have today from surface measurements and what we believe we will be able to do when we have measurements from space. Okay. So real quickly, how do we make the measurements from space? Well, we're going to use exactly the same fundamental molecular physics that give rise to the greenhouse effect. We are going to look at sunlight that will be reflected off of the surface of the Earth and measured then by the spectrometer, by the instrument inside of the Orbiting Carbon Observatory. So as the observatory flies over, it will look down at the surface, see this reflected light, and be able then to make measurements of how that light intensity changed as a function of the path that the light went through. And you recall that the absorption of the light is based on the fact that it can excite these vibrational motions of the carbon dioxide molecule. So we're going to look in places where we know the carbon dioxide molecule absorbs and make measurements there. And by the depth of the absorption, we can correlate that with how many molecules were in the path, because we know, on average, how much light each one of these molecules absorbs. Okay? And so we'll just trace this out and do a relatively simple experiment. Now, it's a little more complicated than that because, by the way, this is an image, an SRTM, a digital elevation map image of the Pasadena area. So there's Pasadena and the Rose Bowl, and we're up here a little bit more. And the column over Pasadena is actually not that different in terms of its composition from the column that we expect to find over Mount Wilson. But we would make a very, very, very different measurement of the number of CO2 molecules in each of these columns. And that's for the simple reason that the light has gone through a shorter path length here or a longer path length here. And so there are just more of these molecules in the path in the column that goes all the way down to the Pasadena floor as opposed to the column that bottoms out at the tops of the mountains. So what we need is not a measure of the total number of molecules in the path, but a concentration measurement. How many molecules are there per unit volume in that total column? Okay? And what we do there is we know that oxygen in the atmosphere constitutes 20.958. You know, we can put out 5 or 6 significant digits, and it's the same concentration at every location, every altitude, every time that you go to make the measurement. And so we use that to normalize the measurements that we make. So by measuring oxygen at the same time as we're measuring carbon dioxide, and then taking a ratio, we then get a normalized measure of the carbon dioxide mixing ratio. And we can then hope to compare this normalized measure of the concentration of CO2 in the column over Pasadena with the column over Mount Wilson. And that way we can make really nice and equivalent comparisons for different times and places without having to worry about, are we just reproducing a really nice elevation or surface pressure map? Okay? So that's the way we're going to go forward making these. For those of you who like a little bit more technical detail, and I know there are the science goobers out there. I see some of you, yes, you can't hide. Okay, so at higher spectral resolution, these are what the absorptions look like of carbon dioxide near 2 microns in wavelength, carbon dioxide near 1.6 microns in wavelength, and oxygen near 0.76 microns in wavelength. Now notice that each of these bands looks different, even for CO2, which is the same molecule. And these fingerprints are what we can use to characterize not only the molecule that's absorbing, but by the depths of these absorption features, how much is being absorbed, or reversing that, how many molecules there are in the path that we saw. So this is, at the instrument resolution of the Orbiting Carbon Observatory spectrometer, the kind of data that we expect to see out. And we will convert that data into concentrations and then be able to think about the carbon cycle science. So we're going to make the measurements from space, as I said, using the same fundamental physics as is causing the greenhouse effect. It's kind of turning the question on its head. We're using this very high resolution to be able to see these individual features here, because that increases the accuracy with which we will be able to make these retrievals. And it also will wind up giving us some other information, like information on the surface pressure or clouds and aerosols that we might see in the photon path that it has traversed between the sun, the surface, and the spacecraft. And that's the way we're going to move forward with OCO. Okay, so I know that's kind of complicated. Everybody good with that so far? All right. Excellent, excellent. You guys are sharp. Now, here's the question you were asking before about, sir. These are maps broken up into regions, and the color scale down here gives you the uncertainty in our knowledge of the flux of carbon coming in and out of each square meter of each one of these regions per year. And it's expressed in terms of grams of carbon per square meter per year. So a square meter is about this much by about that much, okay? And for those of you who aren't quite up to speed on your metrics, even though we converted to the metric system back in the 1970s, yes, for those of you who weren't born, you should only know the metric system. For those of you who were born, you know better, and you know you should know the metric system. It's about 450 grams per pound. A kilo is 1,000 grams. And so 28 grams is about an ounce. So 30 grams right there would be an ounce. Somewhere out here in the orange color would be about a pound. You're talking about 2 pounds at 1,000. Out here, you're talking about 4 pounds of uncertainty in our knowledge of the flux. Now, the crosses here represent these other places. In fact, there's Mauna Loa right there. And there are a number of other observatories that are now making these measurements of CO2 around the world. And there are about 100 of them. So here's what it looks like for January. And if you take all of that background CO2 information and invert it, our uncertainties in the fluxes are quite poor. I mean, we're talking about 2 kilos, somewhere around 5 pounds of carbon uncertainty for each square meter. And it's especially bad over the land areas where we might expect there to be the most activity. So the places where we have large amounts of plants wind up being pretty bad in terms of error. You can see other errors over the oceans are not quite so bad. The other thing that tells us we don't have enough data, so not only that we're making the right measurements, just not enough of them, is that you get areas of really high uncertainty adjacent to areas of much lower uncertainty. That kind of discontinuity is indicative of a system that's trying to be solved with insufficient data. We call this an undersampled system. So we need more data. Now we could go out and propagate millions and millions of surface stations, or we could take advantage of measurements from space, which will provide us millions and millions of measurements on a global scale on a very, very short time scale. We can, for OCO, we'll go completely around the world about every 5 days, and we'll come back to exactly the same place every 16 days. So in about 2 weeks' time, we've done a complete mapping of the Earth. And we've done some simulations, and notice what the errors look like for satellite-based data. Much, much more uniform, number one, much lower, number two, and if we look over the problem zones where we expect to see things, notice we're now talking about errors down around 30 or so grams per square meter per year instead of 1,800 grams per square meter per year. So at least an order of magnitude better, if not 2 orders of magnitude lower uncertainty. And recall, it's that uncertainty in the process that we need to put into our models to be able to forecast the climate in the future better. So we're all tying all these things together. Okay? So that's an advantage. Does anyone know where this is? Rome is a good guess. You're warm. France? France is closer. This is the Seine. And this is Paris. So there's the Louvre right there. If you look really closely, you can see the park where the Eiffel Tower is. This is the scale on which OCO is going to actually make its physical measurements. Each one of our footprints is about 3 square kilometers, about 1.3 kilometers in one direction and about 2.3 kilometers in the downtrack direction. So as the satellite moves along, we will make, every third of a second, we'll make 8 of these measurements. And then the next third of a second, we make 8 more. And the next third of a second, we make 8 more. And so you see how we would map out some place like Paris. And in each one of these footprints, we would have the 3 spectra that we'll be recording. 1 oxygen spectra and 2 different carbon dioxide spectra. So this is the kind of data that we'll be bringing back and the kind of scale that we'll be bringing it back on. Now we're on this very, very fine spatial scale, not because we need to have measurements at that resolution to understand the CO2 or the carbon cycle problem, but because we're trying to see all the way down to the surface, and there's something that can prevent us from doing that. Clouds. Clouds getting in the way. So the smaller the footprint, the higher the likelihood we have of being able to see in between the spaces in times when you have patchy cloud cover. So on partly cloudy days, we still want to be able to make our observations, and it's critical because the interaction of the atmosphere with the surface is what dictates how much carbon dioxide we will see. It's absolutely essential that we see all the way to the surface. And so we're trying for this very small footprint just for that reason. Okay, so now let's talk a little bit more about some science. We go back 2 months now. Although just last Friday, so only 5-6 days ago, we don't even have to go back a full week, the second part of the IPCC report was released. So in February, everybody got together and the science basis was released. And the key thing here is that we now have very high confidence that human activities are causing the world to warm. Okay, this is amazing that you were able to get 2,500 scientists and 1,000 politicians and diplomats together in a room and have them come up with this simple conclusion because it is so extremely contentious. And I just want to highlight the fact that according to the IPCC, very high confidence means that 9 times out of 10, you're correct. So a 90% chance of being correct in this answer. Before, many of you know, there's been even hesitation on the part of many agencies to put forward any kind of assertion about climate change and its link to human activities. And now we've got a 90% correlation between human activity and global warming. Okay, that came out in February. Well, we kind of looked at this before, but we looked only to the present. So now, in 2001, here's what the IPCC was saying about projections of CO2 into the future. And you can notice that there are a number of branches here for a number of different scenarios. These scenarios take into account economics, population growth, technology increases, and what actions and policies we might actually choose to implement. And so for a number of these different scenarios, run through on the order of a dozen models, and forecasting future climate, you can see what the spread is. And so by 2100, our best estimates in 2001 were saying we can anticipate between 550 and 1,000 parts per million of carbon dioxide in the atmosphere, with an uncertainty that's about a factor of 2. Okay? And the corresponding temperature forecasts are for an increase between 1 and 6 degrees centigrade with, for the different scenarios here, now broken out the relative uncertainty. So you could follow up one of the scenarios and see its relative uncertainty there. I wish they had done that for the CO2 scenarios, but that was not part of the study in this time. Okay, so that's what we knew circa 2001. What just came out in February? Well, here's our business as usual scenario. We just keep going on and on and on. And this is the global surface warming, so it would peak out around half a degree centigrade or so. But for a number of different scenarios, here are the uncertainties, and here's the corresponding mean value projected out at 2100. So again, you can see we have the business as usual or just constant propagation scenario at about half a degree, but the other scenarios vary between about a degree and about 3.5 degrees of average global temperature increase. So again, we're seeing forecasts into the future which have less uncertainty now, but still more than I think any of us would like to see. Okay, well, how do we understand some of this emission? The principal investigator, the guy who makes the big bucks, David Crisp, who in fact now, even as we speak, is doing some observing on not Mauna Loa, but Mauna Kea in Hawaii. He can actually look across from one volcano to the other and see the observatory on Mauna Loa. Dave drives this really nice, totally souped up Mazda Miata. In fact, I used to joke with him because he's done so much work on this car that the only thing that was stock on his Miata is the nameplate. And then earlier this week, I went out, he doesn't even have a nameplate on it. There's nothing stock on this car. So it's a Miata for the purposes of our discussion, but it drives very, very nicely, very, very fast. But it's very convenient for us because it weighs, according to this factory specs, 1,007 kilos, which is very, very close to 1,000 kilos or a metric ton. So we can use it and think about a metric ton of carbon being represented by a Mazda Miata. So 8 gigatons of carbon per year is what we're currently putting into the atmosphere from fossil fuel combustion. That is 8 billion Mazda Miatas. That's more than one new Miata every year for every person on the face of the Earth. There are 6.7 billion people on the Earth, according to the most recent forecasts. So 8 billion Miatas every single year of carbon going into the atmosphere. If you want to think about it a different way, a Miata is about 4 meters long. And the circumference of the Earth at the equator is 40,000 kilometers, or the equivalent of 10 million Miatas placed nose to tail around the circumference. Or you take the 8 billion Mazda Miatas, and that's enough to circle the Earth 800 times at the equator. That's a lot of Miatas. Okay, so how are we going to deal with this emission scenario? We've got a lot of problems. Let's look at some CO2 arithmetic. And by the way, those of you who didn't have an opportunity to take one of the handouts that are sitting up in front, I encourage you to take one as you leave. Because what we see here is some CO2 arithmetic. So if we wanted to go from our current level of 380 parts per million to an effective cap that's kind of twice the pre-industrial average, so 2 times 280 is 560 parts per million, what do we need to do between now and then to think about this? So if we take our current emissions rate, which is about 8 gigatons of carbon per year, or the equivalent of 2 parts per million a year increase in the atmospheric CO2, we take what our target is, which is 560. Our current is 380, so it gives us a difference of 180 parts per million. 180 parts per million by 4 gigatons of carbon tells me that we've got 720 gigatons of carbon total emission between now and when we hit our target level of 560, if that's the target we decide that we would like to hit. Okay? Well, you can go a little bit further and say if 8 gigatons of carbon per year is our emission rate, and we're going to hold that emission rate, okay? We're going to hold that emission rate. We've got at the most 90 years before we hit that level of 560 parts per million, and that requires that in the 91st year, we're down to 0 emissions. So we go from 8 gigatons to 0 somewhere in that time. The conclusion that a reasonable person might draw from this is that controlling emissions alone is not going to be sufficient, and that we're actually going to have to do some mitigation. We're going to have to pull some CO2 out of the atmosphere somehow. And so what's shown here and talked about in the CO2 arithmetic paper is as we wedge down in the amount of CO2 that's being released into the future, we're also going to need to capture and store some of the CO2 that's currently in the atmosphere. So we're going to have to do some scrubbing if we would like to hit something like 560 parts per million. Okay, how would we do something like that? Well, here's one way of doing some scrubbing. You can attack the problem at the source, or at the smokestack, as it's called. And you can take the CO2 that would normally just go off as effluents, and you can actually sequester it down into the ground. So you could pump it down into the ground where you'd be certain that it would stay in places like old coal beds or depleted oil or gas reserves. It's not certain. You would have to do some tests first and make sure that the reservoir into which you were pumping would retain the CO2 and retain it for a geologically significant period of time. Okay? Good question. One of the things that's not on this small graphic but is frequently spoken about are old salt mines. That's another place where people have talked about storing CO2. And, oh, this one, shoot, I cut it off. It's also showing on the other part of the graphic is you might think about deep sea storage as well. Okay, so those are a couple of ways that you could sequester and store carbon. Let's do a little bit different kind of math. Let's do some economics math. What would it cost to capture and store carbon? So we have reported capture costs, or current capture costs, shown in these red bars for a number of different techniques here. And this is costs in US dollars per ton of CO2. And most things are coming in the $10, $20, $30, $40 per ton range right now. And the targets, through either optimization or more efficiency or just more usage, would be down in a more affordable range of maybe something like $10 a ton. And so if you look at that, okay, I was using a slightly older value of 7 gigatons of carbon per year. At $30 a ton, it winds up being a $210 billion per year industry to pull CO2 out of the atmosphere. Is that expensive? Well, relative to the 2004 GDP in the United States, which was $11,000 billion, it winds up being about 2% of GDP. The world GDP was about $55 trillion, or 55,000 billions, and the CO2 capture cost would be about 0.3% of the global GDP. So if you think that's a reasonable amount, okay. If you don't, there are a lot of people that are interested in that. We'll talk a little bit more about the economics in a couple more slides. The reason I bring that up is because we've talked about sources, we've talked about sinks, and the Kyoto Protocol is talking about exactly the same thing. So your anthropogenic carbon dioxide equivalent emissions, according to the Kyoto Protocol, should be reduced such that they're down by 5% compared to 1990 levels in the first commitment period, which winds up being 2008 to 2012, right around the corner. Just about 6 or 8 months from now, we're going to have to see people who are agreeing to the Kyoto Protocol start to meet these levels. Okay? You can also think about your net changes, which shall be used to meet the commitments. So that incorporates both your emissions and removal by sinks. And this should be reported in a transparent and verifiable manner. Okay? Well, each country that signed on to Kyoto would have to do its own reporting. But what can OCO do? It can monitor. We can use OCO to verify, right? So let's talk a little bit about that. Real quickly, we can look at some of the culprits. The United States in 2003, was emitting about close to 6 billion tons of carbon per year. Russia about 1.5 billion. China about 4 billion. Other countries to a much lesser extent. What's going to happen? Well, one of the very, very interesting things that's going to happen, if it doesn't happen this year or happened last year, or maybe it happens in a year or two from now, China is expected to surpass the United States as the single largest emitter. So right now, we're more or less even. This is just a breakdown for coal, not total CO2 emissions, but China at about 2.7 billion tons related to coal. The United States at about 2.1 in 2003. By 2025, the forecasts are for nearly 6 billion tons per year from China and about 2.8 from the United States. So you can see that things are changing dramatically. And if you're interested in verifying something, you'd really, really like to know that you're getting good data, not only from the people who are providing it, but you would like to be able to confirm that data. Okay, so that's one of the things we can do from space. We can make measurements globally and hope to provide some information to confirm. So how do we go about quantifying the sources with OCO? Well, we're going to look on regional scales at fluxes, which are both sources and sinks. Actually, looking for sources is a lot easier than looking for the sinks because the sources tend to be stronger and more localized and more variable. So a smokestack is pumping out huge amounts of CO2 when it's on, but when it's off, it's not doing much of anything. And it stays in the same place all the time. So you can imagine that smokestack might be a large industrial plant. It might be a 100 megawatt electricity plant. Lots of different things. And we can track that quite well, much more easily than sinks, which would vary, say, over time and place more subtly for the biosphere or oceans. Okay, fossil fuels, quickly. The amount of gasoline in a gallon contains about 2.86 by mass. 87% of that is carbon. When you burn this in the atmosphere, when you go through combustion, you combine the carbon in the gasoline with oxygen from the atmosphere to make CO2. You accumulate some extra mass, and it winds up that you yield about 8.9 kilos, or roughly 20 pounds of CO2 for every gallon of gasoline that's burned. Okay? We can then think about what's the detection efficiency of OCO. Well, we're designing for a 1 part per million out of this background of 380 parts per million. If we assume that this perturbation, that the emissions are confined to the very lowest kilometer, that would constitute about a 10 part per million increase in that lowest kilometer of the atmosphere is the equivalent to a 1 part per million increase in the entire column. And if we go through the math, 7 times 10 to the 5th kilos of carbon dioxide per each one of these OCO footprints, or approximately 7,500 gallons of gasoline burned would be detectable in a single pass. So the reason I bring this part up is let's look now at California, because our governor has said, yea, verily, you will go forth and you will reduce greenhouse gas emissions. And by 2010, you're going to go down to the 2000 levels. By 2020, you're going to 1990. So California is striving to be not quite as good as Kyoto by 2020, but by 2050, we're going to be 80% below. Okay, so that's a really ambitious and quite good thing from my perspective. All right, so how would OCO measure? These are separate orbit tracks, different flyovers that take place during our 16-day repeat cycle. And they don't happen in this order, but I've just labeled them for you. You can see that there are 6 that go through the area of California. And there's kind of 5 days between this guy and one of its nearest neighbors on either side. And there are kind of 2 days between second nearest neighbors. And so we're sampling relatively frequently. And because of the way that we're making the measurements and looking down, you can see that we do a nice definition of not only what's going on in California, but on the barriers both coming into and going out of California on the basis of the prevailing winds. So we should have a very, very good way to monitor the amount of carbon dioxide flowing through the state of California. And that's going to be really important as we move forward. I should have mentioned much earlier on, sorry for not doing that, that OCO will launch in the year 2008. We're currently scheduled for December 2008, which is the first year of the Kyoto enforcement period. So we'll be able to provide information on that, even though the United States is not a signatory to the Kyoto Protocol. Okay, well, inside California, Los Angeles is a little bit more of a concern for most of the people in this room. If we assume that Los Angeles is kind of approximated by this 100 by 100 degree square that I've laid down over the city, we can go through the math, and the per capita emission in the United States is about 23,000 kilos of CO2, 13 million people in Los Angeles. That leads us to, about 8 times 10 to the 8th kilos of CO2 per day. If we divide that by the 10,000 square kilometers and the number of footprints we get, we find out that the average emission in Los Angeles per OCO footprint is about 4 times 10 to the 5th kilos. Recall that the detection limit of OCO is about 8 times 10 to the 5th kilos, which means that we only need about 4 of our OCO footprint measurements to have a 1-to-1 signal-to-noise detection of what's going on in Los Angeles. And we can make those in 1/3 of a second, okay? Because we're making 8 measurements every 1/3 of a second. So we're already able to measure what's going on in Los Angeles with extremely high resolution, okay? All right, here's the part where I expose myself figuratively. This is my carbon footprint. And I encourage you to go off and think about this. There's a nice site here where you can go off and calculate your carbon footprint. There are some different calculators you can find if you search around on the web. I did mine. You can see it's based on what I use to heat and cook, electricity that we're using at home, cars, other transportation. The huge chunk here is travel. If you fly locally within, say, the state of California, it's not so bad. If you fly cross-country, it gets worse. If you fly internationally, it's worse still. And so the majority of my carbon emissions per year are due to airline travel. And it winds up being about 20,000 kilos of CO2 per year on average. And that compares more or less well with the estimated per capita average in the United States. A little bit lower, not a lot, but there you go. So I encourage all of you to go out and evaluate where you stand. Let's come back to the economics again, real quickly. People find a big kick out of putting dollars to this, so let's go through and do it. And if you look at how CO2 emissions per ton were trading in 2005 and 2006, you see that in the European Union, where they are regulating this already, it was trading somewhere around, let's say $30 per ton of CO2 emissions. That's an easy number for me to use. The 8 gigatons of carbon being emitted per year winds up, because we're pulling in some oxygen from the atmosphere, winds up being a little bit more, actually. But we'll go back and just do it on a per ton basis. So 30 times the 8 gigatons is a $240 billion per year industry. $240 billion per year that's not yet fully realized. But if the whole world went on a trading scheme like this, it would be. All right? Well, that's a lot of money, but how does it really compare to the big boys? So let's look at the Fortune 500. ExxonMobil, $339 billion in 2006 revenues. Walmart, Sam Walton, he knows how to make a business run, $315 billion per year. CO2 emissions would come in at Fortune 3 if it were a full-blown global industry trading at about $30 per ton. Okay? Better than General Motors. It's a real big hit, and this is one of the major reasons that a lot of people who are not scientists are very, very afraid of putting in regulations and controls against this, because they're just doing simple calculations like this and looking at the dollars that come out on an annual basis. And they're wondering, where is this money going to come from? Okay? If you put another zero here and you put another zero down here, you're now talking about something that's the size of the Japanese domestic product, right? $1 trillion per year kind of numbers. Okay, so that gets us to our wrap-up. We've talked about a lot of hot topics. We've talked about some cool science. I think that it's pretty fair to say that CO2 is already a ubiquitous problem, and I'm sure you're just going to hear more and more and more about it. It's produced every time you light a fire, every time you turn on the ignition of your internal combustion engine, literally every time you breathe, CO2 is involved. Okay? The primary objective of the Orbiting Carbon Observatory is to quantify the geographic distribution of natural CO2 sinks. I should also put up there their temporal variability. We're also interested in how they vary over time of year, not just place. And more than that, not just time of year, but from one year to the next. What's the interannual variation? But in a standard mode, OCO will be able to look at XCO2 variations as small as 1 part per million, which corresponds to something like 7,500 gallons of gasoline. So if you have a traffic jam, you can imagine that we'll be able to look down as we're flying over and actually detect what's going on in a big traffic jam where you'd have that much fuel being burned. It's only 2 tanker trucks full of fuel, not very much at all. So we can easily detect urban areas and traffic patterns, and we gave you a little bit of demonstration of the kind of monitoring and verification, information that OCO can provide for not only looking at California and the United States, but also you could apply that to anywhere in the world you were interested in looking for CO2 emissions. So thank you very much. And before we go on to talk about some other questions, I'd like to just say that I'm extremely fortunate to stand here before you tonight because I get the fun job of coming out and talking about this. But there's a huge group of people both within the science team and within the OCO project, who are actually working extremely hard to realize this vision of a satellite for not only NASA, but for the entire United States and the world. And so here's a picture of our science team. We had a meeting down at Caltech just in February. You can see some of the people here. I would also like to ask that members of the OCO project team or anyone who is contributing to OCO, please stand up at this point in time, because there are a number of you out there in the audience. Don't be bashful. Please stand up. I want everyone to see. Yes. Thanks to all of you. Thank you again to all of you, not only for working so hard with us to make this a reality, but I know you guys are not working the standard 8-hour days, and for you to take the extra effort to come out here tonight and support this is very, very much appreciated. So thank you to the audience, and at this point I'd like to open things up for questions. Gentleman in the back again.
Yeah, you mentioned your scenarios predicting the variation in temperature. Does that just take into account CO2? Because there are other greenhouse gases besides CO2.
Yes, that's correct. The question is, in the simulations that are run for the IPCC evaluations, are we talking just about CO2, or is it incorporating things like methane and ozone and what might happen from water vapor and other greenhouse gases? The answer is, I'm sorry if I didn't explain this clearly enough, they are expressed in units of carbon dioxide equivalents. So every molecule is assigned what's called a global warming potential. And that's based on the number of infrared absorptions that it has, the strength of those infrared absorptions, and that's done then on a per molecule basis. And you can multiply that strength by the relative number of molecules that are in the atmosphere, and you get the net impact to the global warming potential. And that's all then normalized. CO2 is given a GWP, a global warming potential of 1, and so everything is normalized to units of CO2. Thank you for asking for that clarification. There's a question here.
Since the United States was not a signatory to the Kyoto Pact, how receptive do you think the international community will be to the OCO offering the monitoring activities of the Pact?
Okay. The question is, since the United States has not signed the Kyoto Protocol, it's not in force for the United States at this point in time, how will the international community react to the data that we will be providing from OCO? Number one, we will provide this data regardless of what the international community thinks. Okay? We are committed to providing this data. One of the things, if I'm a negotiator, that I would really like to have, whether or not I've signed this treaty, is I would really, really, really like to know whether you, who are a signatory, are actually abiding by your commitments. And if I have the data with which to make that assessment, and you do not, then I have a very, very good negotiation position. And so we're interested in obtaining that data whether or not the Kyoto Protocol is in force for the United States. And I may get in trouble for saying this, but let me just back up and say that we showed some information during the course of the discussion that demonstrated that controlling the emissions is not going to be enough, that we were going to actually have to think about scrubbing CO2 out of the atmosphere to reach some level in the 500, 600, maybe even 700 parts per million range. If you look at what the Kyoto Protocol requires, it requires a rollback to 1990 levels and then a 5% reduction against those. That's just slowing down the inevitable. That's not taking the emissions down to zero and talking about removing carbon from the atmosphere. That's just slowing the point in time at which you pass whatever your target value for atmospheric CO2 concentration is. Okay? And one of the things that we've found over time is that that nature is very good at adapting. And people are very, very good at adapting. If you think about 200 years ago or even 1850, what the United States was like, according to what we know from the history books, it was very, very different than what it's like today. We can adapt on that kind of 100-year time scale. We can even adapt on a tens-of-year time scale. But adapting in single years or in months to some pretty massive changes that we're looking at is not something that we're very good at. And so we need to have in place some longer-range thinking so that we can address this problem before it becomes something that is perhaps prohibitively costly to address. Let's go over here. Yes, ma'am.
How much public access will there be to your data? If I wanted to know a fairly CEO-friendly or absent CEO place in the United States, will there be a website I can look at? Will you be making regular reports?
Okay. The question is, will the OCO data be freely available publicly? And will we be making regular reports on our understanding of the data? Okay? The answer to the first question, will it be publicly available? Yes. That is, in fact, one of our highest level requirements with NASA. Not only that we deliver the data and make it publicly available, but that we do so in a very short period of time. We're required to deliver our first CO2 products within 9 months of commissioning the observatory. So people shouldn't have to wait for this information. And it will be located in what's called the Physical Oceanography Distributed Active Archive Center, or PODAC, here at JPL. And if you have a web browser, you'll be able to point to PODAC, point to the OCO mission, point to the data products, and pull out whatever you would care to look at. And we'll also be putting in information there for how to use the data. And we'll put in some graphics so that people don't necessarily have to download 50 gigabits of numbers before they get any useful information out, because we're all much better at looking at pictures than at ones and zeros. Thank you. Over here, yes.
And much earlier, you showed graphs that showed correlation between temperature fluctuation and CO2 fluctuations over 40,000 years. What are the theories behind why you had those fluctuations up to recently 100, 200 years ago?
Okay. The question is, The question is, why did we, when looking back at the ice core data that stretch back not only over 40,000 years, but over 400,000 years, why were we seeing the correlations between CO2 and temperature? Why were they going up and down? And then why, in the current era, have we gone away from that oscillation? Over the last several 100,000 years, the Earth has been in a series of glaciation cycles. And so what you're seeing there is mostly the advance and retreat of ice sheets and how that's been influencing the climate.
What caused that?
I'm not an expert in this area, but as I understand it, there were some interesting precession wobbles in the Earth's axis and what's going on in our orbit. And it's thought that that is giving rise to some of these events. Let's see, is there anyone in the audience who we can tap on?
Solar variation, output of energy.
Solar variation is another theory that has been put forward, yes, and outputs of energy. Ross, can you help out? Ross Salowich, one of the OCO science team members.
The prevailing thought is it's driven by variations in Earth's orbit, as Chip alluded to, driven mainly by Jupiter and also by the gravitational influence of Saturn. That's called the Milankovitch cycle. Most people believe that changes the seasonal distribution of insolation, which drives changes in CO2, which drives changes in temperature. There's a minority view that the 100,000-year periodicity is driven by the time it takes to build big ice sheets, and then they collapse upon themselves. That's the Peltier hypothesis from Ohio State. But most scientists believe it's driven by variations in solar radiation hitting the Earth, ultimately regulated by Jupiter and Saturn.
Yeah, so that's a great set of questions, and I'm sure that Ross and others would be glad to answer. Let's see, there was a question up here. Yes?
You're talking optimistically there'd be sinks, but then pessimistically that it's hard to find them because they were diffuse. So you have some strategies for trying to track down the things that would be sinks for CO2.
Yes, the question is, sources wind up being relatively easy because they're easy to see. They put lots of CO2 into the atmosphere. The sinks are more subtle and generally spread out over time and space. What strategies do we have to find them? It actually winds up that to do a good identification of a CO2 sink, you need to run all of the concentration information that we would be measuring into a very sophisticated model that can move the air around the Earth and trace it both forward and backward in time and understand where an air parcel was interacting with the surface at what point in time. And then it becomes a series of nonlinear differential equations that I'm sure you're wonderfully excited about. But going back and pulling out these model results and finding out whether a certain region of the surface was a net source or a net sink at any given period in time. And we can run these models. These models, by the way, are very, very similar to the models that forecast the weather for us every day. Except instead of running over a 24, 36, 48-hour period, they run over 6 or 8 or 12 months or even longer. So climate is really just the weather in a place over an extended period of time. And that's the kind of modeling that we would use. Good question. Here?
Back to that same correlation between CO2 and temperature.
Yes.
Is there a similar correlation with other greenhouse gases? And would it be possibly more efficient to remove smaller quantities of a different gas?
Okay. The question is, do other greenhouse gases show correlations with temperature as CO2 does? The answer to that question is yes. And the second part of the question is, would it be more efficient to think about removing other greenhouse gases from the atmosphere rather than carbon dioxide? And the answer to that is maybe. CO2 is such a predominant contributor to the greenhouse effect in terms of what human activities are doing, that's really the area in which most people have focused. If you wanted to adjust the greenhouse effect the most, what you would actually want to do is to adjust the amount of water vapor in the air. Water vapor winds up being the strongest driver of the greenhouse effect in the Earth's atmosphere, but it's really, really hard to do that because now you've got to clamp down on the entire hydrologic cycle of the Earth. And so every place there's a pond or a puddle or an ocean, you're going to try and regulate how much water is evaporating up into the atmosphere. And that's a much more problematic event. Something like methane might be possible to pull out, nitrous oxide might be possible to pull out, but their overall contributions to the radiative forcing are much, much smaller than for CO2.
So then if water vapor is the worst, if you were using like contrails, does that contribute more because they're actually up in the atmosphere? And also like hydrogen, if we do switch like fuel cells or hydrogen, that produces water as the exhaust, so that make it worse.
This is getting into be a little bit more detailed and a little bit off track, so maybe we can talk about this after some of the more general questions are done. Okay? Great. We have a question here, Kyle.
You've spent a lot of time talking about the anthropogenic sources and stuff of CO2, which was primary focus here, but a primary focus of the mission is to look at natural sources and sinks. Are you going to have the kind of resolution required, for example, to look at migrations of sources and sinks through forested regions as growing seasons change? And can you cast some of the terms that you put into human and anthropogenic source context into those natural sorts of phenomenon that we'd like to track?
Right. So if I can really quickly give a synopsis of the question, it is, we've talked about anthropogenic combustion sources of CO2. Will OCO also have the ability to provide information that would enable us to characterize natural sources of CO2? And the answer to the question is yes, we will have that kind of resolution and bring back that information. But the natural sources wind up being more diffuse, just like the sinks. And they're smaller magnitude than the industrial or the combustion sources as well. So again, it requires slightly more sophisticated treatment. You can't just look at individual soundings and kind of say, yes, that one's high in CO2, and look, we're over a city or we're over a power plant. That makes good sense. If you're looking at broad regions over forests, say Siberia, the taiga, or over the Amazon, again, it would take one of these more sophisticated atmospheric transport models where you would put the CO2 concentration information in and propagate the model both forward and backward in time to see where the air had been and what parts of the surface it had interacted with. So again, it would require a little bit more modeling and analysis, but yes, we should have the information content to be able to extract that knowledge as well. There was a question. Okay, we'll go here.
Is burial the only or best option for removal, and what are the impacts of that?
Burial is not the only or best option for removal. A great option for removal is creating carbonates, minerals, hard rocks, which just requires running your CO2 through a little bit of base. Lye, for instance, is a great way of doing this. And you can make big chunks of stuff that you can then go off and dispose with how you would care to. The deep ocean is another sequestration that people are very interested in, although there is a finite time for cycling of ocean water from the deep ocean back to the surface. It's on the order of 1,000 years or so, and so that might be more problematic. Also, if you had some event on the bottom of the ocean that suddenly brought that water up to the surface, you'd have some difficulties. Also, with deep sea sequestration, you have the problem that you've got carbon dioxide, which would then form into this kind of gelatinous liquid phase, a big goo, would cover the bottom of the ocean. And so you're covering the ocean floor, making it an anaerobic or lacking oxygen environment, which would not be very pleasant for some of the life forms down there. So there's another environmental impact that one would have to consider. Again, CO2 is very inert, so it's hard to change it into something much, much more difficult. And the reason we're really in this problem right now is that over millions of years, the carbon reservoirs have been changed from biological sources. So CO2 in the atmosphere has been pulled out, converted into biological forms. Those have been, over the eons, compressed into fossil fuels, coal, oil, trapped natural gas. And what we've been doing over the last few tens of years is very rapidly releasing that carbon that was sequestered over many, many millions of years and putting it back into the active part of the system. And so that's one of the reasons. It's not the amounts of carbon so much, it's the rate of change at which this is happening that we're having trouble dealing with. Let's see. Abraham, you helped out, so.
I was just wondering if you knew if Mother Nature has shown any signs of adapting to this rapid increase of CO2?
Okay, great question. Has nature shown any signs of adapting to the increases in atmospheric CO2? And there are both positive and negative answers to this question. Positive answer is, as you get a small temperature increase, you tend to increase the growing cycle. And this is especially effective at higher latitudes, further north or further south away from the equator. You increase the growing season, you increase the amount of time that the plants have to take up the extra CO2. This is known as CO2 fertilization. And so they actually grow more. Now, you get to a point where you're heating too much, and the limiting factor is not now the length of the growing cycle or the amount of light that you have available, it's the amount of water that's available. So as things become too hot, you're evaporating away the soil moisture, and you're forcing the system, the ecological system, into a water stress situation or a drought type of situation. And during these situations, the actual amount of growing time is decreased. And we've seen both parts of this cycle within the last 15 or so years in North America. In the early 90s, there was a lot of increased growth, a lot of new moisture. From the mid to late 90s through to about 2004, there was actually an extended drought period. We saw the amount of CO2 uptake decrease over time. With the return of moisture conditions in 2004-05, we've now seen a return of increased CO2 uptake. So the ecosystems can respond on these kind of timescales, and it's just a question of how much extra CO2 or how much extra heating we see going into the system. There was another question over here? Yes, in the back.
If it were possible, what would doubling the plants on the planet, what effect would that have?
Okay, the question is, what would the effect of doubling the plant life on the planet have in terms of the CO2 concentration? And I don't know about doubling. That's a lot of biomass to introduce. But there are a number of people who have said we're already behind on planned forestry, and we should be reforesting basically every open square meter of land surface area that will accept a new tree, because that's going to be the way of really doing the sequestration in the most cost-effective manner. So that's a great question. You can imagine that there are lots of people in the various forestry services that are already thinking about how to do this. We have a question over here. Yes?
Has there been any political opposition from maybe the international community about having this data collected?
I would say quite the contrary. The international science community is looking at CO2 and drooling over, getting this data. They are absolutely, positively eager to go. And in fact, as the lead for the OCO science team, that makes me a little bit scared, because many of the people on the OCO science team are working really, really hard to get the system in place, to get it all tested out, and to get it launched. And we haven't had the opportunity to work as much on some of our science thinking and our science computer programs and stuff. And our international colleagues are working really hard on that. And so when the data do become publicly available, there are many of them that are basically ready to ingest the data, punch a button, and watch the answers start to come out. So the international community, at least from the science perspective, are very, very eager to have this information. I should also add that the Japanese space agency, JAXA, is putting together a mission called GOSAT, the Greenhouse Gas Observing Satellite, which will fly approximately the same time as OCO. It will make measurements of carbon dioxide, methane, and carbon monoxide. We'll use a different technique. It'll be in a different style of orbit. And we're already working very, very closely with the GOSAT team to make sure that we understand how to cross-compare the measurements that OCO will make with the measurements that GOSAT will make, because the last thing that we wish to do is to confuse the international science community by putting out two data sets that are nominally measurements of the same thing, but that don't agree within their mutual measurement uncertainties. And so one of the things that's inherent in this process and incumbent upon us as the science team is to make sure that we properly characterize not only the accuracy of our data, but the uncertainties associated with every single one of the measurements. And there will be millions and millions and millions of those. Okay? Question here.
The CO2 has been growing quite a bit recently, and I don't think anybody sees this stopping very fast. So it's going to keep growing and growing and growing. What happens if this thing gets like 3-4 times as much as there is right now? You know, I've heard about a tipping point. What happens? What is a tipping point, and what happens after a tipping point?
These are all excellent questions, and I've included information like that in other talks that I've given to this type of audience. Let me try and address some of those things. Number one, is there a tipping point? Yes. Do we know where that tipping point is? Not really. There have been some evaluations made about what happens at certain levels of CO2 concentration in the atmosphere. For instance, it's thought that at levels approaching 400 or so parts per million that you begin to jeopardize coral reefs. There's a potential for enough increase in the ocean temperature that you would bleach coral reefs, which are very, very sensitive to temperature changes in the water. So we're very rapidly approaching a decision point with respect to coral reefs, and I don't think we have the power to put the brakes on the CO2 to stop it from going through 400 parts per million, which will happen in less than 10 years from now at an increase. We're looking at about a 2 parts per million per year increase in the rate, so 380 to 400 is going to happen in less than 10 years' time. Okay, I don't think we can stop that. So coral reefs are probably already in jeopardy. If I recall correctly, at around 500 parts per million, you start talking about potential impacts to glaciers. And
Can you clarify something about that?
yes,
The coral reef is based, it's a temperature thing, right?
Yes.
So it's not a CO2 thing.
it's not acidification of the ocean, but if you're tracking CO2 and temperature together, if there's the concomitant rise in atmospheric temperatures, which would then raise the sea level temperatures, when the sea level temperature increase is somewhere just below about 1 degree C, then the coral reefs are in serious jeopardy. At the 500 part per million level, you start talking about ice sheets and whether or not ice sheet accumulation or decrease is going to be influenced. And this is a big, big deal because, as was mentioned earlier, ice sheets are growing on a 10,000 kind of year time scale. So if you have something that's going along in this direction and has a great deal of momentum, you suddenly reverse that momentum. You're talking a very long period of time before it would change and reverse back again. So if you start affecting and impacting ice sheet growth or ice sheet decay, that's something that will perpetuate for many thousands of years into the future. At the 600 or 700 parts per million level, there are discussions going on about whether you can affect what's called the thermohaline current, which is the giant conveyor belt that runs through all of the Earth's oceans and is basically a heat engine that moves heat energy from the tropics to the northern latitudes. The Gulf Stream, for instance, is part of the thermohaline current, and it's moving hot water or energy from the tropics, from the Gulf of Mexico. It's transporting that to the North Atlantic There's thoughts that if you have CO2 in the 600-700 part per million range, you might induce some kind of climate change events that would shut down or significantly alter the characteristics of the thermal halide current, which would have dramatic effects. For instance, if Europe didn't have that flow of warm water coming in, they would be much, much more icebound or colder than they currently are, because they're very far north relative, for instance, to the United States. So those are the kinds of effects that one might have to take into account. Question here.
Where does your 560 target translate into the parts per million or billion of carbon?
Yeah, so 560 is, you're talking about affecting ice sheets. 500, 560 parts per million is in that range. Maybe a low probability of affecting the thermal halide current, but as you get higher and higher in atmospheric CO2 concentrations, you increase the probability of affecting all of these systems.
My question, maybe I didn't explain it, but you had said your target for, maybe it's the Kyoto, you picked the 560, and that may be on the emissions of carbon or something else, and how does that translate into the temperature of the Earth or the environment?
Yeah, the 560 parts per million is a very artificial value. It's just chosen because it's twice the pre-industrial value, or twice the pre-industrial maximum of 280 parts per million. And so if you accept that it's a reasonable value to set as your target, then you would stop there. If you think that a reasonable value is something like 3 times the pre-industrial value, or you don't need to tie it to the pre-industrial value at all, you can come up with justifications for any value, and it might be an economic justification, a scientific justification, an economic, let's take another economic. If you drive the temperature up too much, you're going to lose snowmelt, for instance, in the Sierras. And so now all of a sudden we have a water resource problem here in the state of California. If you don't have the snowmelt, you don't have the drinking water, you don't have the agricultural water, we've got some serious implications going on there. That's something that's very likely to happen within the next few decades, and we need to adjust for that. Let me take the question here that was
I heard scientists talk about the tundras melting, and in the tundras there's a lot of decomposed plant matter, and that might turn into CO2, so that could raise it much faster than the current projections. How do you feel about that scientist's opinion? I don't think it's very popular, but I've heard of it.
Yeah, no, this is a very common opinion. The question is, if we have melting of the permafrost at very high latitudes, especially in the northern hemisphere, and there's all this decayed vegetation that hasn't really had a chance to decay, it's dead vegetation, hasn't had a chance to decay because it's basically frozen all the time, and instead of growing a glacier, what you're really just doing is increasing the layers of peat, okay? So you get these peat bogs that form. If that suddenly warms up and melts and thaws, it can decompose. If it decomposes rapidly, then we have a situation that's much more akin to looking at industrial sources of CO2, although it would be a natural source. And that's something that worries many people, because not only do you get CO2 out of these peat bogs, but you get huge amounts of methane. And methane is 23 times more effective on a per molecule basis than carbon dioxide in terms of global warming potential. So if you were to emit a huge amount of methane over a very short period of time, especially in an area like the Arctic, which is very, very vulnerable ecologically, then you could experience some potentially severe impacts. Sure.
Do you have any idea how big the reservoirs of the peat moss is?
No, I don't have a good idea of the exact values of those. I'm sorry. There was a question here. Yes?
Yes, has anybody approached like Exxon to ask them to do carbon sequestering in their abandoned oil fields or something like that?
The petrochemical companies are very aware that this is something that there is a growing desire to see, both from within their own corporations and from the wider communities. There are some corporations that are taking a much bolder approach and are actually advertising that much more than others. So I'm not going to mention any names, but those of you who know these things can think about that and search for information. But yes, the companies are very, very interested in. Okay, I'd be more than happy to speak with people who would like to stay around, but I've been given notice that we are to terminate the questions at this point in time. So once again, thank you very, very much for coming out this evening. It's been a great pleasure.